By now you should have watched the video on the introduction to the concept of moles. So now let's take a look and see how we can use moles to assist us with chemical reactions. So let's start out with a very basic reaction, one that we've used on a number of different occasions, and that is the reaction of hydrogen and oxygen to produce water. What do those coefficients of 2 in the reaction refer to? It's 2 molecules of hydrogen and 1 molecule of oxygen producing 2 molecules of water. So if you wanted to carry out this reaction in the lab, we would need to somehow count out 2 molecules of hydrogen and 1 molecule of oxygen. And of course that would be incredibly difficult because they're so tiny we have no way of actually plucking out a single molecule of anything. So in chemistry we commonly use a different approach, which is called counting by weighing. Instead of counting out a large number of individual molecules, we can simply figure out how many we have by weighing them. So let's take a look at an everyday example. I don't know if you guys have ever watched Roadrunner cartoons, but again, referring back to my childhood, loved Roadrunner cartoons. And Wile E. Coyote was always buying things from the Acme company, and one of the things he bought were Acme earthquake pills. So suppose your boss at the Acme plant comes to you one day and says, I need to know how many earthquake pills we have in stock, and I need to know by this afternoon. Well, you've got thousands and thousands of those pills in the warehouse, and there's no way you can get them counted that quickly. So the alternative is to count them by weighing them. The way this approach works is we weigh all the pills together to get the total. Then we weigh a single pill and simply divide the total by the mass of that one pill, and that tells us how many we have. So we'd start out with the total weight. We have 5,000 pounds of pills in the warehouse. Since the pills are weighed in grams, each pill weighs 2 grams, the first thing we would do is convert that into grams. And then, knowing the mass of the individual pill, we can figure out that we have 1,135,000 pills. It would have taken a lot of people days to measure or to count that many pills, but using counting by weighing, it's a very quick and easy thing to do. Now let's see if we can apply this counting by weighing idea to our chemical reaction. So we need 2 molecules of hydrogen, and if we take a look at the symbol for hydrogen, you may remember I warned you guys all semester, don't use those red numbers until chapter 9. That red number, of course, is the atomic mass. That's how much a hydrogen atom weighs in AMUs, about 1.0 AMUs. So if we have 2 molecules of hydrogen, that's 4 atoms of hydrogen, and that would be about 4 AMUs. Now 4 AMUs is a very tiny amount of weight. You may remember that an AMU is only about 1.67 times 10 to the minus 24th grams. That's about a trillionth of a trillionth of a gram. So we can't weigh something that tiny on our balances. Our balance only goes out to the nearest hundredth of a gram, and this is a trillionth of a trillionth of a gram. That's about 10 to the 22nd power smaller than our balances are able to handle. Same problem with the oxygen. Oxygen has a mass of 16, and so an O2 molecule would weigh 32 AMUs. 32 is still incredibly tiny compared to the balance, which can only weigh as low as 100th of a gram. So what we like to do in chemistry is the same kind of thing you often do at home when you're cooking, and that is if you're having a lot of guests, you sometimes will increase the scale of your recipe. And we can do the same thing with chemical reactions. We can increase the scale as long as everything gets increased by the same amount. For example, instead of using 2 molecules of hydrogen, we could use 24 molecules of hydrogen. We could scale everything up by a factor of 12. So now we would have 48 AMUs of hydrogen, and that's incredibly tiny. 48 is very small compared to a trillion. So a dozen is clearly not enough. We need to scale this reaction up even further. Maybe we could use a gross. A gross is a dozen. That's 144 times larger. But even 2 gross of hydrogen molecules would only be 576 AMUs, which again, compared to a trillion, that's nothing. So we've got to keep going even bigger. How about a ream? We normally think of measuring paper by the ream, but you can measure anything. A ream is 500 objects, whatever those objects happen to be. But even 500 reams, if we are 500 times the scale, we still only have 2,000 AMUs, and 2,000 is nothing remotely close to a trillion. So the problem we had, of course, was that there were no groupings large enough for what we needed to do. A dozen, a gross, and a ream, they work great for many things. Dozens work well for eggs and donuts. A gross is great for, say, pens and pencils you're buying at Office Max. Reams are excellent for paper. 500 sheets of paper is a convenient amount. A dozen eggs is a convenient amount. So all of these groups were invented for convenience. Just like every unit that we have, somebody had to invent it at some point. So when we need a unit or a group and there's not one in existence, we simply make a new one up. The AMU, for example, you may recall, they came up with the AMU because they needed a very tiny unit of mass to be able to measure something as small as an atom. Because atoms and molecules are so tiny, you need an awful lot of them before you have enough to actually see it and be able to weigh it on a scale. So scientists said, you know what, we need a new unit. And they came up with that unit that was discussed in an earlier video, which is the mole. So a mole is a lot of items, 602 billion trillion items. And this grouping is known also as Avogadro's number. So if we used 2 moles of hydrogen and 1 mole of oxygen, would that be an appropriate amount to measure on our balances? Our balance can measure anywhere from about 1/100th of a gram to 800 grams, so we would like to have enough that would be convenient, enough that perhaps we could put in a beaker or a flask and weigh on the balance. So the question is, how much would 2 moles of hydrogen molecules actually weigh? Well, that sounds like a conversion problem. So we start out with our 2 moles of hydrogen, and we'd like to figure out how many grams that would be. Well, the first thing we can do is convert moles into molecules. Whether it's molecules, donuts, it doesn't make any difference. There's always Avogadro's number of whatever item you have in a mole. We can then take the number of molecules and use this conversion. We know that a molecule of hydrogen weighs 2 AMUs, so if we multiply it by 2 AMUs per molecule, we can figure out how many AMUs there are. The problem, of course, is our balances don't measure in AMUs, they measure things in grams. So our final step is we would want to change AMUs into grams. So if we use our conversion that we came up with earlier in the semester, and we do the math, why, lo and behold, it comes out to be 4 grams. So 2 molecules of hydrogen weighed 4 AMUs, and 2 moles of hydrogen weighed 4 grams. What an amazing coincidence. What are the odds that those 2 numbers would come out the same? Turns out the odds are real good because it was designed that way. Let's take a look at an everyday example here using donuts. Now let's suppose that a dozen was actually 16 items instead of 12, just for purposes of this illustration. So let's suppose that a dozen is 16 items. And we wanted to find out how much a dozen donuts weighed. If we knew that 1 donut weighed 2 ounces, we'd like to know how many pounds a dozen donuts would weigh. So the ounces is sort of like our AMUs, and the pounds is like our grams, and the dozen is sort of like our mole. So we start out with our 1 dozen donuts, and then we multiply it by the number of donuts in a dozen, at least for our illustration here. We can then, using the weight of each donut, figure out how many ounces of donuts we have, and finally we can convert that to pounds, and why, amazingly enough, a dozen donuts weighed 2 pounds, and a single donut weighed 2 ounces. So the number actually stayed the same, just like it was with the hydrogen, where the number of AMUs in one molecule turned out to be the same as the number of grams in a mole of a molecules. So a dozen and a mole are simply different size groups. Now the reason that worked is because the number of AMUs in a gram is essentially the same as the number of objects in a mole. If we take our conversion 1 AMU equals 1.67 times 10 to the minus 24th grams, like any conversion, we can invert this. So we could put it upside down, and it turns out that 1 gram is actually 6.02 times 10 to the 23rd AMUs. Why, it's Avogadro's number again. So if the number of objects in a mole and the number of AMUs in a gram are the same, it's like our example here, where the number of objects in a dozen and the number of ounces in a pound were the same. That's why it remained 2 in each case, and that's why it worked out so nicely with AMUs and grams. It was designed that way. It wasn't a coincidence. Now, what makes that really nice for us is, if you look on the periodic table, the atomic mass of the element, if you're considering a single atom, then an atom of neon would be 20.18 AMUs. If we had an entire mole of neon atoms, it would be 20.18 grams. The same is true with every element on the periodic table. An atom of magnesium, 24.305 AMUs. An entire mole of magnesium, 24.305 grams. And the same thing is true with cobalt. 58.933 AMUs in an atom, 58.933 grams in a mole. So let's go back to our original equation here, the hydrogen and oxygen reacting to form water. If we use moles in the equation, if 2 molecules of hydrogen weighed 4 AMUs, then 2 moles of hydrogen would be 4 grams. That's a convenient amount, easily measurable on our balance. A molecule of O2 weighed 32 AMUs, so a mole of oxygen molecules would be 32 grams. Now, if we carried out this reaction, how much water do you suppose we would get in this reaction? It turns out to be 36 grams. Now, how were we able to figure that out so easily? And the answer, of course, is the law of conservation of mass, which says whatever you put into a reaction has to come out the other side. So if we combined 4 grams of hydrogen and 32 grams of oxygen, we would have to get 36 grams of water. Now, in a little while, on our next video, we're going to learn another way to do that. There's another way to determine how much of the product you're going to get other than simply adding up the masses of each of the reactants.